Greetings, everyone. Thank you for tuning into our webinar today. It's titled LiDAR and Powerline Mapping. Which mapping solution is right for my business? The presentation for today will cover a bit of background on the history of the North America bulk electrical system and a couple of events that have precipitated the industry that we know today, the resulting policy changes and the NERC and its new mandate. We'll also cover deliverables for the Powerline industry as it relates to NERC, the asset mapping classes for transmission, distribution, and inspection. And finally, we'll look at sensor solutions, platforms associated with those sensor solutions, the sensors themselves and their inherent benefits, and custom sensor configurations. And finally, some conclusions. Currently, there are almost 500,000 kilometers of high voltage transmission lines in Canada and the US that converts to about 300,000 line miles. So it's no small task to manage such an enormous network. But let's jump back briefly to the beginning. In the United States in the 1920s, utilities formed joint operations to share peak load coverage and backup power. In 1934, with the passage of the Public Utility Holding Company Act, electric utilities were recognized as public goods of importance and were given outline restrictions and regulatory oversight of their operations. The Energy Policy Act of 1992 required transmission line owners to allow electric generation companies open access to their network and led to a restructuring of how the electric industry operated in an effort to create competition in power generation. No longer were electric utilities built as vertical monopolies, where generation, transmission, and distribution were handled by a single company. Now, the three stages could be split among various companies in an effort to provide fair accessibility to high voltage transmission. However, two transformative events occur that highlight the dependence of the North American industrial engine on the reliable production of electricity. The first is the blackout of 1965. On November 9th, a massive electrical blackout occurs in the North American Northeast. It affects both the northeastern United States and the province of Ontario, Canada. Almost 30 million North Americans find themselves without power, and over 850,000 people are trapped in the New York subway. The cause is determined to be an incorrectly programmed safety relay, which causes a disconnect during increased power demand at a plant in Niagara Falls, Canada. Ontario Power is subsequently transferred to other lines, overloading them in the process. As a result, the National Electric Reliability Council, known as NERC, is formed in the wake of this first large-scale blackout in June of 1968. Its mandate to promote the reliability and adequacy of bulk power transmission in the electric utility systems of North America. However, compliance is recommended and not enforced. 38 years later, another blackout occurs on August 14th, 2003. Striking at 4:10 p.m. during the height of evening rush hour, there is a widespread power outage in the same geographical location as the 1968 outage. In this case, 50 million people are affected and is the most widespread blackout in the history of electrical civilization. The cause? An aging electrical grid, a series of technology flaws, and a few overgrown trees lead to a cascading series of outages stretching from New York City to Ohio and up into Ontario. A blackout which is later determined to have been preventable and for which immediate actions must be undertaken by both the United States and Canada to prevent a similar event. The economic impact, $4 to $10 billion. As a result of this, a joint task force is created with both US and Canada participants that same year. Stakeholder and public input is included in early 2004, and the final report is released in April of 2004. The report provides a thorough investigation of the causes of the blackout for recommended actions to minimize the likelihood and scope of similar events in the future, and concludes that in the absence of enabling legislation in the United States and complementary actions in Canada and Mexico, the NERC lacks legal sanction authority to enforce compliance with its reliability rules. The 2003 blackout is a clear signal that voluntary compliance with reliability rules are no longer adequate. NERC and the regional reliability councils must therefore assume firm authority to measure compliance, to more transparently report significant violations that could risk the integrity of the interconnected power system, and to take immediate and effective action to ensure that such violations are corrected. With this report in consideration, the U.S. Congress passes the Energy Policy Act in July 29 of 2005. Some of the significant changes associated with this policy are the repeal of the Public Utility Holding Company Act of 1935, incentives and loan guarantees for alternative energy production, and advancement of innovative technologies that avoid greenhouse emissions, expanded jurisdiction of the Federal Energy Regulatory Commission to appoint and oversee an electric reliability organization, or ERO, and that ERO is certified by FERC to adopt and enforce mandatory standards for the reliable operation and planning of the bulk power system throughout the United States. These mandatory standards and requirements replace the current voluntary rules of the time and results in increased investment by and in transmission facilities ever since. In 2006, the North American Electric Reliability Corporation is certified as the new ERO for the United States. Canada follows suit and adopts the same NERC reliability standards. Canada and the United States have since worked together to harmonize the implementation of mandatory reliability standards as developed by a single ERO. There are now over 100 standards which have been developed which cover all aspects of reliability, including transmission operations, resources and demand balancing, facility design and maintenance, system planning, communications, training, cyber and physical security, and emergency preparedness. Of those 100 or more standards, transmission vegetation management has been identified as a critically important one, with a corresponding mandate to prevent vegetation-related outages, which could lead to cascading. To do so requires a systematic examination of vegetation conditions on the active transmission right-of-way, to identify and document existing and future hazards, modeling existing and predictive locations of conductors, whether it's due to sag and sway for rated conditions. In the past, much of this was done by sending field crews to traverse the right-of-ways, manually documenting and subsequently clearing problem areas. As we know, the most effective method to rapidly collect, document, and measure right-of-way assets is to use remote sensing technologies. However, the use of LiDAR has evolved to become the de facto technology for the capture of 3D information from which direct measurements can be made in the office environment, as opposed to the field. Power lines are generally broken into two classes, transmission and distribution. The larger transmission lines carry high voltages ranging from 60 to 150 kilovolts to extremely high voltages as high as 500 or even 700 kilovolts or more. From the generating station to substations, where step-down transformers reduce the output voltages to enable distribution to the community and urban centers. Smaller service lines emanate from the distribution network to your homes and businesses. These are generally lumped into the distribution class, but are of much lower voltages still. The size and structure of the towers are largely a function of the voltage that passes through it. The larger the voltage, the larger the right-of-way, and the further away from the ground are the conductors for safety purposes. Asset management is really about collecting, measuring, interpreting, and actioning information about the asset for safety and longevity. There are many measures of asset management that are performed within the industry, both NERC mandated and otherwise. With transmission lines, we often look at line routing exploration, as-built asset inventory, geolocation of poles, conductor sag analysis, and of course vegetation management initiatives that include vegetation clearances for growing and falling analysis, speciation, risk assessment, and conductor clearances to roads, buildings, and surrounding man-made structures. On the distribution service side, it's looking at conductor and transformer health, integrity of the insulators and the circuitry, tower footings inspection, guy wire conditions. Both NERC mandated and otherwise, these are some of the more common ones. When it comes to technology options, there are really 6 primary sensors that are integrated or combined in some form or another, depending on the platform and application requirements. These include RGB imagery, either nadir, oblique, or both, 4-band imagery. NIR imagery, when combined with RGB imagery, creates a 4-band composite image of additional information. And the collection of 4-band imagery enables us to create normalized difference vegetation indices, which is used for analysis of vegetation health. Thermography or thermal sensors enable infrared inspection of transformers, connections, and conductor hotspots. Coronas caused by excessive electric fields surrounding a conductor is a significant waste of energy. And so identifying these can reduce the corrosive effects caused by gaseous discharges to the environment. HD video is used a lot to enable the selective capture analysis of high-resolution imagery from any point on the right-of-way following collection. Meteorological management systems are used for catenary modeling of power lines to determine the amount of energy that can be transmitted under varying load and line conditions safely. Sag tension values for the line are determined with the ancillary input of wind velocity, temperature, and other meteorological parameters. And finally, LiDAR. As stated earlier, LiDAR has become the de facto technology for the 3D mapping of complex structures. So it comes as no surprise then that its inherently orthorectified data and high precision accuracy make it ideal for computer-aided measurement and analysis of power line catenaries, as well as the structural mapping of surrounding vegetation and objects that may pose a hazard to the right-of-way. When it comes to sensor selection, platform choice is always an important consideration. Aircraft typically cost less than helicopters to operate, but require necessarily higher altitudes. However, recent increases in sensor performance are now making previously unviable platform options very much a practical and cost-effective choice for certain deliverables of power line data collection. For long-distance transmission line surveying, helicopters have long been the platform of choice and continues to be the case. However, small aircraft are now starting to also participate in this segment by as much as 40 to 50% in some geographic areas, reducing collection times while also maintaining high point density at speed and improving overall collection efficiency. A recent poll of around 400 registered attendees in one of my Powerline LiDAR webinars our series reveals that this number is closer to 50%. Mapping of the distribution and service network is not the same as flying a long linear corridor. So for this kind of data collection, the networks are often quite complex, necessitating the need to fly a block survey. Also, given much smaller conductor sizes, superior detection is required. For these kinds of surveys, the higher performance sensors normally associated with wide area mapping at high altitude are becoming preferred. This is because they have both good target detection capability at altitude, but also much higher productivity and cost effectiveness than what a helicopter could otherwise provide. For asset or line inspection requiring health and integrity validation, high resolution LiDAR imagery is the norm. And this is best accomplished from low flying helicopters or UAS sensors. Beyond visual line of sight applications are starting to pave the way for increased use of drones for asset inspection. Before the inspection of many spans of power line assets requiring multiple sensor options, helicopters continue to dominate. So RIEGL Laser Measurement Systems has designed and produced high precision survey instrumentation for the commercial surveyor for almost 40 years. Whether it's transmission line mapping in mountainous environments at high altitude, or broad area mapping of distribution networks, or even low altitude flying of power lines for vegetation management initiatives or asset inspection, RIEGL has a sensor that is purpose-built for a variety of power line applications and required platforms. Incorporating application-specific scan patterns and required measurement precision enabled by its advanced research and expertise in full waveform deconvolution and 3D coordinate measurement, RIEGL sensors are able to provide the highest quality data in the most productive ways possible. This chart plots the maximum altitude performance of the various airborne laser sensors in RIEGL's ALS product portfolio, where maximum flying altitude assumes full footprint interception of the laser beam and reflection of the emitted laser pulse by a 20% reflective target. This next chart reveals the sensor configurations available specifically for various applications of Powerline surveying. While the larger sensors are already purpose designed for aircraft installation, the smaller sensors have been packaged to enable off-the-shelf total solutions for helicopter and UAS installations, including LiDAR sensor, optional cameras, sensor pod, heli mounts, UAS integration kits, flight management systems, INS, GNSS inertial systems, and front-end data processing workflows. The achievable point density of the various RIEGL sensors using various platform scenarios assume, in this case, a 1 centimeter wire diameter and a target reflectivity of 20%. Much higher altitude performance may be possible for the same laser emission rates for larger and more reflective targets. Alternatively, much greater density may be possible for the same altitude for larger and more reflective targets. However, as you may have noticed, the operating flight altitudes are much lower than that identified in the previous slide. And this is because there are many factors that affect a sensor's ability to detect power lines. This necessitates a much lower flying altitude than what would otherwise be considered flying hard targets alone. And these include sensor performance characteristics such as laser wavelength, laser energy, receiver sensitivity, detection thresholds, beam divergence, and the resultant footprint size on the target. The conductor characteristics such as wire diameter, material composition, and related reflectivity. So now that we're familiar with the top level performance of the various sensors as a function of the platform, let's take a look at which sensor solutions are optimal for each asset class. This way we can review what sensor configurations best meet your application needs in more detail. For long distance surveying of as-built transmission line assets, we recommend downlook sensors that are capable of high rotational scan velocities to enable optimum point distribution when flown at speed. These sensors include our VQ1560 Mark II, the 580, and the 480 Mark II. For aircraft platforms, and the VUX 240 packaged with our VP1 pod, which I'll explain later, for helicopter installations. For the mapping of distribution networks in urban environments, block survey collection is preferred. For this, we recommend our VQ1560 2 sensor again, available with an embedded 150 megapixel RGB and NIR camera for 4-band imagery co-collection, as well as a unique crossfire scan pattern. 1560 enables a multi-look perspective of the scene from a single sensor pass to all but guaranteed detection and coverage of complex networks. Alternatively, the VQ480 580 Mark II can be used for smaller area collections. For line inspection, we recommend the VP1 pod with VUX 1LR or the standalone VUX 1LR and VUX 240 sensors for UAS installations. These sensors have the range performance to enable collection on either platform for maximum flexibility and scalability. Here's a closer look at some of the specifications associated with each sensor solution for each asset class. The VQ1560 is RIEGL's flagship product and represents a hybrid LiDAR and high-resolution imaging solution with 2 independent laser channels. It has exceptional long-range performance and is typically flown on larger aircraft at altitude. It is also used for wide area survey applications such as the USGS 3DEP program or statewide collections. However, more recently, this sensor has been repurposed for users by flying distribution transmission line collection, largely because of its crossfire scan configuration enabled by the dual laser system contained within a single sensor enclosure that's fully gyro stabilized. The crossfire scan configuration provides both a forward and aft look angle to simultaneously cover both the front and rear of transmission towers. Because of the 1560's 2 laser channel, it has an extremely high emission rate and therefore high point density capability. For point density without adequate point distribution is not conducive to consistent data across the entire FOV. The 1560's crossfire scan pattern solves the homogeneous point distribution challenge by employing a very fast rotating polygonal scanner that can lay down as many as 600 lines per second. This extremely high scan rate is required to take advantage of high emission rates. So don't get fooled by high emission rates from sensors that utilize slower scan speeds or larger FOVs and lesser scan patterns, where the point distribution at the center of the scan is vastly different than at the edges. Density without uniform distribution is not conducive to quality data sets that are consistent throughout the entire swath width. And this is of particular importance for single flight line passes along a corridor. Vegetation management initiatives also benefit tremendously from the improved vertical density that the crossfire scan configuration of the 1560 provides, and the resultant matrix point pattern that only the 1560 offers. Because the 1560 can fly much higher than most other sensors, its laser beam divergence and resultant footprint on the ground of wire is necessarily smaller. We want to have resolution as well as point density, and so a smaller beam footprint is important. Like all wide area sensors on the market today, the 1560 uses a beam divergence of less than 0.18 milliradians. That translates to a laser spot footprint of less than 6 centimeters from 1,000 feet AGL. The 1560 also comes standard with a high accuracy OEM inertial navigation system from Planix, the AP60. For long flight line lengths, this is important for maintaining heading accuracy over long distances. Sensor parameter or calibration stability is an often overlooked consideration, so when flying long linear corridors, it's imperative that a sensor maintain the same level of accuracy regardless of the parameters selected. One can't rely on redundant overlapping data strips that are generally not available to crush out any residual errors or minor deviations when flying corridors. All RIEGL sensors are well known to maintain a single consistent calibration regime for all available parameter sets. It's a lot harder to fix these variations as parameters change in post-processing versus collecting stable data to begin with. Finally, as sensor performances increase, the susceptibility of sensors to false returns from atmospheric or other effects increases. RIEGL has developed a solution to actively suppress these false positives during collection, or they could be also removed during the post-processing effort using spatial filtering methods. The VQ580 and 480 Mark II sensors are much smaller and are designed for smaller aircraft, but like the 1560, are also designed to fit inside a gyro-stabilized mount if desired. They utilize a 2 megahertz pulse repetition frequency that translates to 2 million shots per second, also with a fast scanning speed, but this time only with a single laser channel. Combined with a rotating polygonal mirror, the 480 and 580 sensors lay down a nice parallel grid pattern on the ground for evenly distributed points across the entire FOV. Based on the smaller size and lesser laser energy, these sensors are used most often for distribution areas of smaller size. The only difference between the 480 and the 580 is that the 480 uses a 1550 nanometer wavelength versus the 1064 nanometer wavelength of the 580, allowing you to fly at much lower altitudes if necessary from an IP safety perspective. These smaller sensors are available as either complete solutions or as transceivers ready to be integrated with your preferred flight management system or inertial system using your third-party vendor of choice. They really are that flexible. So we also offer a sensor controller API to make the process a whole lot easier for a custom solution tailored to your choice and enabling technologies. The VUX 240 is RIEGL's latest survey-grade compact LiDAR system that bridges the gap between the VUX 1LR and perhaps the VQ 480-580 Mark IIs. It is extremely lightweight, less than 4 kilograms, but has a 75-degree downlook field of view, similar to the VQ 480-580 sensors, but with an incredibly fast scan rate of 400 lines per second. It can really distribute the high laser emissions at low altitude for best-in-class XY point distribution on ground and power line assets. Finally, the VUX 1LR is a compact sensor design used quite extensively for line inspection, largely due to its 330 to 360 degree planar field of view. It is the first survey-grade LiDAR sensor for small UAV installations where the mean takeoff weight is less than 25 kilograms. This sensor first came out in 2015, so it has a tremendous amount of field experience. The VUX LR and its variants has been used as a platform for upgrades ever since and has excellent range performance for low altitude applications. So whether it's on a UAV or a helicopter, it can be used on either platform. The large global FOV of the VUX 1LR is ideally suited for proximity flying to Powerline assets on either side of the right-of-way, as opposed to having to be directly above them. This is the perspective of a pilot when proximity flying parallel to the right-of-way with the VUX 1LR. As you can see, this wouldn't be possible without a large FOV sensor. RIEGL offers the VUX 1LR in 3 configurations. The first is a standoff transceiver for integrators, and the second is a system version with OEM INS solution for faster integration on whatever UAS or helicopter platform you choose. And then 3 as a fully integrated soup to nuts solution with flight management system, inertial navigation system, high resolution cameras, and our VP1 pod. The VP1 is a carbon fiber pod designed specifically for the rapid dismount on any rotorcraft equipped with a dovetail mounting system, which we can of course provide. Like the VUX 1LR, the VUX 240 is fully compatible with our VP1 pod for a plug-and-play helicopter installation. So whether it's a Bell 206, 407, 429, AS 350, 355, H125, an MD 369, 500, 600, or a Robinson R44 or R66, or even a Cessna 172, 180, 182, 190 aircraft, the VP1 pod is compatible really with a tremendous number of platform options requiring no internal cabin modifications, bolted in and go. The VP1 is also capable of being compatible with your helicopter's flight management system, streamlining the interface between LiDAR operator and LiDAR sensor with our API for data acquisition. If an onboard flight management system is not installed, RIEGL has options to provide a strap-down flight management system or a pre-configured onboard acquisition laptop. Optionally available with the VP1 are various camera configurations depending on application requirements. For download look collections centered over the right-of-way, nadir and oblique camera configurations are available using various third-party vendors, including the Phase 1 IXM, FLIR's Tau 2 thermal, and Sony's A7R3 and A6000. For proximity flying adjacent to the right-of-way, larger oblique FOV options ranging from 129 degrees and even up to 213 degrees are available as well. So while RIEGL does offer fully integrated total solutions, customers do have the option to integrate and create their own custom configurations by purchasing our LiDAR sensors as components. Whether it is a VUX LR or VUX 240, VQ 480 or 580, one can specify your own preferred flight management system, your own INS GNS solution, and your own camera combination to create truly unique solutions. And a good example of this comes from 2 acquisition companies, Quantum Spatial and Aerial Filmworks. By utilizing 2 VUX sensors, Quantum has angled the fore and aft orientation to create a crossfire pattern that can be realized similar to RIEGL's VQ 1560 scheme. This has the benefit of mapping both sides of the asset in a single pass for a wholly complete data set. Here's the setup that Aerial Filmworks has also configured. Notice the canted orientation of the VUX scanners, providing a fore-aft scan geometry that provides complete coverage of the asset with a single flight pass. So in conclusion, whether it's transmission corridor distribution network or line inspection, LiDAR with supporting imagery, RIEGL LiDAR sensors are really the ultimate foundation of a Powerline mapping solution. We at RIEGL take the guesswork out of piecing sensors together by offering rapidly deployable off-the-shelf solutions or in-house expertise to help you assemble your own. We also are looking forward to the completion of our expanded US sales and service center with dedicated hardware and software technicians, enhanced calibration facilities, and optional fly-in surface capability. We are committed to keeping you airborne and operational 7 days a week. I hope you enjoyed this presentation. For more information on these and all 3D mapping solutions, please send an email to info@rieglusa.com or call us at 407-248-9927. Have a great day.